Okay, welcome everyone to our final mentorship session for the 2023 Building AM Design Competition. Today we have Dave from PADT. He's going to be talking to us about using the full additive advantage and kind of tying everything together that we've learned throughout the last couple of weeks. So with that, we'll go ahead and turn it over to Dave.
All right, thanks. Let me go ahead and share my screen. All right. Perfect. So is that coming through, Garrett?
Yep, we can see it good.
Perfect. All right. Okay, so I'll go ahead and get started. So this is the session on using the full advantage of additive manufacturing. So I'm Dave Dietrich. I've been in the space of additive manufacturing, or in the world of additive manufacturing, prior to it even being called additive manufacturing. So I've been working in this field since 2004, when I came into Boeing Research and Technology. I worked for Boeing for 12 years, and my primary role at Boeing was to develop and mature additive manufacturing technologies, both polymer as well as metal. So I did that for a number of years, like I said, about 12 years or so. And then I had the opportunity to go to Oak Ridge National Labs as a Boeing employee and work with a lot of the really talented researchers in the area of additive metals at Oak Ridge National Labs for a couple of years. And then after that, I was hired away at Honeywell Aerospace, where I led a design team doing additive manufacturing design for Honeywell on a number of different components, satellite systems to valving systems to, so all sorts of different aerospace applications. So a lot of the content that you'll see today is content that was delivered to major aerospace companies, just in terms of design thinking and how to really try to leverage additive manufacturing to the best of your ability. So that's a little bit about me. At the end, we'll have some time for questions, where you feel free to chat in some of your questions, or ask your questions directly, and we'll be sure to address those as we go. All right, so let me go ahead and get started. So one of the biggest things about additive manufacturing is that one thing to recognize is that several different companies that exist in the area, and whether it be in aerospace or automotive, or whatever industry they're in, they all sort of reside in different maturity levels of additive manufacturing, or their knowledge of it. Most companies, if you look at this chart, this is a well-known model for understanding the value chain of additive manufacturing. Most companies are sort of in the bottom, where they're using it for rapid prototyping and tooling, and they're simply just sort of printing jigs and fixtures, or they're using it to do some sort of design prototype to check fit and form and function. And they're kind of just using it at that level, and that's broadly how it's well known. Some companies have moved up this building block. As you go up from the bottom to the block to the top of the block, you drive more value out of the technology. And so some companies have realized this and moved up to sort of direct part replacement, where they used to make low rate injection mold parts, and they've realized that maybe it's cheaper to make them additively for low production volumes or something like that. So they've kind of learned that that's a better approach. So some companies are kind of at that stage, and then other companies have realized that, well, you gain more value out of the technology when you start to integrate different components together into a single complex piece that can be printed additively, and that could be either polymers or metals. And so then they move into kind of a part consolidation phase. And so some companies are in that journey at their stage of the maturation life cycle. And then some companies begin to realize, well, what if we just start designing for the technology from the beginning? Blueprint definition, it's a new product line that cannot be manufactured any other way. Let's start with design principles for additive manufacturing in mind from the beginning so that we can truly leverage the technology to its highest level. And so typically the way I've seen this work is, and there's some confusion. Some companies will try to say that that DFAM is, and I think maybe you learned this in some of the previous training material, is that DFAM is just modifying sort of existing components and structures to be able to match the technology. So that means, like walls can only be so thick, or holes need to have support material in it, or something like that. Well, that's more of an MFAM, or modifying for additive technology, additive manufacturing. DFAM, on the other hand, is where you're actually truly designing with the technology from the beginning, and that you're not taking an existing product and retrofitting it for AM, but rather from the beginning designing with AM in mind for the full intention of the product. So as you kind of move up this building block, you're driving more value out of the technology, and you're gaining more in terms of lightweighting as a value proposition, or you're gaining more in terms of your value of the AM technology itself, and whether that could come into the form of lightweighting, that could come in the form of cost per part, that you could drive a lot more value out of it as you keep moving up the blocks. Okay, so this is a well-known model, and then I did copy the source here if you want to see sort of where this is known, but this is well known in the industry at this point. So as I was mentioning, the MFAM, this includes sort of the modified rules, or how to take apart and modify it so that it will be print correctly and that you won't have challenges during the printing. And I think you've already been shown this in previous training, so I'm not going to go into this, but just know that that's sort of where this falls in the building block. Okay. So let's start by thinking about, what does an optimized AM part look like? This is really kind of a thought experiment here. Like, when you look at this part in your mind, kind of consider, do you think this is an optimized AM part? Like, if you saw this part on the left that is conventionally welded, the sort of support bracket, and you looked at the one on the right, in your mind, you immediately think, oh, well, that's been optimized for AM. So, kind of be thinking that in your mind, is this truly an optimized part? Well, chances are the answer is that it's unclear whether it was fully optimized for AM or not, or whether somebody took the part, redesigned it through some topology optimization in it, and printed it, and then now it's kind of a marketing showpiece. Do those loads really match that load path, for example? Did the simulation truly show that was the efficient load path, and does it have enough material there? How do we know that it has enough material in that load path to be able to satisfy the loading criteria of each of the individual kind of flanges? So the answer is maybe not. It may look like an optimized part, but it may not have been. This is where you get into all of the things you've been taught before in these sessions about the simulation and understanding running topology optimization, and when to run topology optimization, understand the simulation behind that. Then you'll know for sure if you know that work has been done, then you'll have more of a clear idea if it's been optimized or not. Same thing with this. Is the one on the left optimized? Again, it looks like it has been, but not really if you look more closely. It looks like it has been light weighted. So they've taken bulk geometry and sort of honeycombed out the areas of bulk structure. But if you look closely around the flanges, those are all still solid. The flanges are still sort of taking the same tapered effect that they had before. And if you look, what really gives it away is it's not truly optimized. If you look on the mounting feet, you can see that where those mount, that's all solid material. Does that need to be solid? Depends on the clamping loads. There's a lot of questions there. If you look on the right, this is another example of using topology optimization of a part, but then perhaps there's wire bundles going through it. This is getting a little bit more optimized. You're thinking more multifunctional now, because you you're thinking about the light weighting effect, but also sort of how wiring can be routed through the channels, because now you're thinking more that the part is not just a structural member, but it's also carrying some other function. In this case, electrical wire harnesses. So this is maybe leading yourself more towards an optimized design, but maybe not truly there yet. Adding function is great, such as cable carrying. The more you can do this sort of thing, the better. Another approach is biomimicry. You may have heard this term before. It's simply emulating nature in your design. So understanding how nature functions and then applying the rules and principles that nature has used in your everyday sort of problems. In this case, this is an injection mold tool with conformal cooling lines inside of it that have to keep the tool nice and cool during the fabrication process. In the upper left, you see traditional cooling lines that have been, sort of bored through the entire plate as just a single shot. Well, that's not incredibly efficient. It may have worked. Probably they just would oversize those boring holes in the past and gotten away with it. And then there's another approach where maybe you have kind of a standard conformal structure where you do cross drilled holes that are then plug welded, and you're able to make some sort of more complicated geometry that kind of hugs the internal feature definition a little bit more. That makes your part a little bit more more efficient from a cooling standpoint. And then if you look at figure 3, this is kind of a standard conformal system as well. This is where they would kind of jacket the internal feature with a passageway and then sort of run a pipe through it. Again, it's a little bit more efficient than the first 2 figures. But then this particular example, they use biomimicry in this design to understand kind of how this leaf works and how it is, cooling itself through nature. And by using that as an inspiration, they were able to sort of drive off different channels from kind of a manifolding system through that sort of leaf structure to drive more conformal cooling inside of a part. So this was actually this was developed by the New York State Energy Research and Development Authority. And it was basically for the company called Harbeck, I believe, that used FEA on a number of these different design iterations. So this is a great example of full kind of getting closer to that optimization pattern. Now, when we talk about additive manufacturing specifically, what tools can we use just right out of the box to make things easier and more efficient? Well, many of them are things like ISO gridding. And ISO gridding, an example of that would be like the image on the far right, this pattern feature. This is a typical aerospace kind of approach. This has been used for centuries or decades at least for light weighting in NC machining for aerospace structure. But don't forget, you can do the same thing easily with your AM parts, even conformally, so that they don't have to be flat. Latticing structures, cellular features, latticing structures here, cellular features here. Kind of, again, removing bulk material that existed previously to satisfy kind of these manufacturing constraints. You're not constrained with a lot of the geometry here. So you have the freedom to be able to do this. What other tools can you use? Novel thermal management features, where you're using really complicated sort of heat sink patterns that couldn't be manufactured before easily. Sort of radial thermal control situations. So again, more features that you have at your disposal if you're going to be using additive manufacturing from the get-go. What software tools exist that can generate these features? Well, for topology optimization, or the ability to sort of make this structure, right, this organic looking tissue sort of structure, you can use obviously a number of different software solutions. InTop is one, Altair, Inspire, ANSYS, TopOp package, Siemens, Tosca, PTC, Creo, and then Autodesk. Most of the major CAD systems like Autodesk, PTC, Siemens, most of them have kind of built-in topology optimization. Some work better than others. It's kind of a newer field, so they're all trying to kind of one-up each other in an arms race of topology optimization. So they're all working on it. It's getting better as each one works. InTop is a software that's dedicated to just topology optimization. So it is it's not trying to do CAD at the same time as some of these other ones are. So it tends to work a little bit better for in-top applications. For lattice structures, like these shown here, again, most of the CAD packages have this kind of have these features built inside of them. So Autodesk Fusion, PTC Creo, Siemens, SolidWorks, CATIA, and then with the exception of Materialize Magics, which is a traditional additive manufacturing software package that's used during the whole value chain of software packages to create a product. So, basically you use the Materialize Magic software as an interim step between going from CAD to your AM machine. So that's a software that can also generate some lattice features as well. Here's just a few examples on the metallic side of just images of different sort of features, gyroidal features, just showing some images, more kind of compliant structures where you can kind of compress and move some of this material. Keep in mind, you can design in your compliance with additive by using some of these features. So if you need to have a part sort of move around a little bit or rebound, don't worry about sort of a gasket, or you may have used that separate part as that sort of function before. We can get rid of that separate part and integrate that into the design now using some of these more novel features for compliance. Diamond structures, for example, more latticing systems. You can get very small and very intricate with these things. You're basically limited by the spot size in metal for the laser of about 10,000ths of an inch. So you can go quite small in terms of your feature detail. And here are just some of the other structures out of TI-64 that you can see just examples of. 3D honeycomb structure. So maybe you have a torsional load case. Perhaps a 3D honeycomb may suffice instead of a typical sort of traditional pipe section. So whereas you may have been inclined before to make it out of a pipe section, if the whole thing it will be an additive solution, you're thinking about DFAM up front in the design process, why not try to lightweight that if it's just going to take torsional load cases? So think of like an axle, for example, or something like that. Doesn't need to be fully solid just because you've always used pipes for axles for many years. Doesn't need to be that. So think about sort of the design function from the beginning, and we'll walk through an example of how to do that. Now if it's carrying some sort of fluid, obviously this wouldn't work, but that's why you have to kind of deconstruct your requirements and then build up sort of your design from scratch, thinking about AM in mind from the beginning. Another good example is multifunctional design. I love multifunctional design. My favorite example is this water faucet here, where it's actually carrying fluid through the structure itself. So through these tubes, the fluid is kind of moving up through the faucet and then out the top. I think you can buy this. This is commercially available. But this is a perfect example of its structure, and then it's also carrying fluid simultaneously. Tubing with built-in air gaps for insulation for additive, for example. Here's another good example of this is just a simple T strainer. I mean, it's not an AM example, but it's just one more example of multifunctional design where it's the T strainer and the mixing spoon all in one, serving multiple functions as a product. So just keep in mind, we want to try to drive this sort of system level thinking in the design from the beginning. So let's take this this approach. So this was an actual use case that was done on an aircraft where they took a bracket that was basically fastened to a composite outer mold line. So basically the actual it was actually on a wing assembly, and then this was just a linkage. And so traditionally, this design was done with a bracket that had a specific weight of 330 grams. It was just an assembly. So this kind of shows the assembly weight. This included the fiber mount, the high locks, and everything else involved. So the load case was 35 kilonewtons for this. So a topology optimized design was created to then replace this. So this is kind of an example of where I was showing before. Is it topology optimized or not? Is it truly optimized? So in this case, they were able to save some weight. They shaved some weight out of it. They were able to get it down to about 1,200 grams. So, about a 41% weight saving. So most people would be pretty happy with that. They'd stop there and say, yeah, this is great. But if you start looking at the function of what this is doing, this is actually just anchoring something to another piece. Can we not think about an integration beyond this? And so, what if you rethink this whole strategy from the beginning? And so this would be kind of IMFAM. You're sort of modifying an existing structure for AM, but DFAM is this next piece where you're thinking about how this is all being what you're trying to do functionally. And this solution is to integrate the design. The bracket is no longer really needed because now the sort of tie rod is now integrated directly into the structure, and then there's now just sort of a ceiling cap that goes in. So now that bracket weight is gone completely. So most trained designers will kind of stop here, but this is why clean sheet design thinking is really important, because you can go beyond that. If you take an existing structure and kind of iterate on that, you're only going to get a suboptimal sort of weight drive or weight performance or value equation. If you rethink it from the beginning, from the design, and rethink how things are manufactured, you're going to be able to achieve that next level of optimized design. All right, so let's kind of walk through what I mean by, kind of thinking about things from the beginning. First, so this comes from a good paper that's out there. I've included, by the way, on all these slides references so that you can go download all of these different, these different articles for reference. But this is a great paper that kind of talks about how to integrate AM design from the beginning. And as with most designs, and in this case, the drone contest, right? You have a requirements list that you've defined. You want it to do so many things. You want it to have so much payload. It's at first it's a little abstract to identify the essential problems that you would have in the conceptual design phase, but then you need to establish functional structures and then sub-functions that need to come from that. So in terms of sort of the drone competition, think about how you know each structure functions. Is it multifunctional, like I showed examples before, or is it just simply serving one purpose? The overall, so you're identifying that in this stage. Then you're going to search for working principles to sort of fulfill the sub-functions. And additive empowers you to do a lot of things, but additive isn't the answer to do everything. Okay, so it's a tool in the toolbox. Keep in mind that if additive cannot satisfy your functional needs, then obviously you should move to more conventional manufacturing purposes. But the next stage is then combining working principles into working structures, selecting the suitable combinations between sort of AM, non-AM, what works best to drive that part count reduction, to drive that weight down, to make your design the most efficient. And then firm up into principal solution variants, so different concept ideas, and evaluate those against the technical and economic criteria that you've defined. And then you come up with a principal concept. So again, you're kind of just driving through different stages in your design. So you take sort of so if you kind of decompose this more in terms of how AM walks into this whole path, basically it deconstructs into four main sections. You're going to functionally decompose your idea, and then what you're going to do is then look at what's called AM ontology and what AM offers from a material standpoint, from a machine standpoint. How large are the machines? How many materials are offered in that type of machine? What type of machine is it? Is it metal? Is it polymer? Blah blah blah. All of that kind of rolls into mapping functions and how AM design principles then now can influence your decision and how that design kind of evolves. And then you're going to go to the next stage, which is stage 3, which is then combining these design principles into a working structure. And then from that, you create a concept. So I'm going to walk through an example. This may be a little confusing at first, but I'll walk through an example to sort of showcase this. So again, here's the AM ontology that I was mentioning. You're basing it into what sort of AM processes are available, what materials are available, what the design principles are, and what the functional structure looks like. Here's a good walkthrough. So in this case, this is sort of a a little fluidic microreactor. So the first stage that I mentioned. So if I go back to the first stage was functional decomposition. So in this case, you start decomposing functionally what this device needs to do. So you import. It needs to import a liquid, contain a liquid, and then guide a liquid. And then you have sort of your different colored paths showing what needs to happen. Each liquid has sort of a different color being shown. It needs to then mix the liquids together, display this visually so somebody can see the sort of the liquids being mixed, and then guide the liquid and then export the liquid. So within this, volumetrically, you have to be able to import, contain, and guide this liquid. And then, this, so basically this is just a functional diagram you're decomposing this into. And then you bring this into your design principles database. So let's talk about the things that I had just talked about earlier in this discussion. So you have to think about how you're going to connect this geometry. Okay, so what does that mean? Is that going to be a standard thread, or can you use multiple materials to incorporate a seal? Use only one port to avoid the need for sealing. Try to break down and reduce the part count as much as possible using AM. Use internal channels and so forth. And then you go to stage 3, which is, if you remember from the chart, stage 3 is then combining AM design principles into a working structure. And then you kind of list out each of the subfunctions, what they're doing, and then you can apply the AM design principles to each one. So you're going to adjust the geometry for connection in this case, use only one part to avoid the need for scaling. So you're going to do some of this multifunctional integration that I was mentioning. You're going to use internal channels because you can with AM. You're going to use complex geometry because you can with AM. So you're just kind of showing each individual function, importing liquid, containing liquid, guiding liquid, mixing liquid, and then how AM satisfies these different subfunctions. And then it goes to the final stage over in stage 4, which again is creating the concept. So then at this point, by using these design principles, you can start sketching up your ideas of how this would look. All right, so then if you go to the next slide, it kind of shows an example of this in practice, where you basically deconstructed those different subfunctions of what you wanted this device to do, and then how you used AM to then achieve those solutions. Okay, moving on. So that's sort of the basic ideas of how to go into the DFAM, all the way up to the sort of the DFAM principle, or designing from the beginning. So we've covered now in previous sort of training, you've covered how to just use AM in general, and then now this example kind of exposes you on how to deconstruct things from thinking about blueprint definition of AM from the beginning in your design. And now we're going to talk about how you can even take AM even further beyond just DFAM. So there's another box on top of this, which I like to call AM Nirvana, which is quite entertaining terminology. And what this is basically there's a lot of advancements happening in the space of additive manufacturing right now that is on the material science side. So all of the optimization that's been done relative to DFAM has been based on sort of the limitations of what the machines can produce, and then how the material interacts with that machine, and the limitations of the materials with the machine, the specific 3D printing AM machine. And so right now in the field of in national labs and academia, there are, and even in industry, there are some examples where companies are driving up the value chain even more by coupling multifunctional DFAM, which I just talked about, with advancements in material science. So adding new materials, and I'll talk about these different advancements in machine parameter optimization, and all sorts of really cool things that are happening in the field of AM right now, where you can take all of this new level of optimization and add it to things I just previously talked about, designing for, where you can reach a whole new level of optimization, or what I call AM Nirvana, which is full optimization. So what's some examples of this that's happening? If you've heard about functionally gradient material, what this is a really cool way, and this is enabled by AM, although you can do it in conventional manufacturing too, but AM makes it a little bit easier. This is the ability to make a part that is 100% one material, and then have it gradually transition by percentage as the part is being constructed to a completely different material on the other end. So in this case, this was a particular part, and it's using directed energy deposition as the additive manufacturing machine. Where in the way this AM machine works is it has a laser beam that's guided down and through a lens, and it's melting a metal pool of powder feedstock that's blown into a coaxial nozzle. And so it's known as directed energy deposition. And what's really cool about this is the feedstock that you feed into the system, you can blend the different ratios. So you could have all titanium at first, and then you could start to dial back the titanium and then add about 15% tungsten. And then in this particular case, this shows multi-layer gradient blends and kind of what you see from a microstructure standpoint when you do it. And then where you then reach 100% tungsten at the top. Now, what this would allow you to do is some really clever different design principles where you could have a part that, it was maybe really low cost in one portion of the part, like maybe a steel, and then maybe it went to a higher performance part, like an Inconel or something like that on another part or another feature of the part. So maybe you needed hardness in one area of a part, and then you needed it not to be super expensive for the entire part. So then you needed it to be something cheaper on the other end of the part. So that's a level of optimization that is that's currently being explored in a lot of the academic circles at the national labs, and then also commercially. So that's a really cool new, and it's also on the polymer side too. You're seeing different blends of polymers being adjusted through filaments in FDM. So you have different ratios of materials. They're kind of being blended together to achieve different functions. So this is a really, new space of material science that can be applied to sort of the design principles we were talking about earlier. Another area of interest, again, at the national lab level, is microstructure manipulation. So for additive metal parts in the powder bed system, being able to tailor the grain structure to orient certain ways. This was some research that was done a few years ago. And if you just looked at the part, you would just see like a big block. You're holding it in your hand. But if you looked under, basically an orientation map, or you're able to look at the grain texture, you're able to see they were able to manipulate the grains so that in certain cases they could spell out the letters DOE. So this was done by the Department of Energy. So that's why they had to spell DOE, because they funded it. But this just showcased the ability of using the laser. And all this is just a trick with the laser. You're applying a different parameter set of the laser to specific areas. So if you think about this, you could apply this to maybe, if you think about features in a part where, for example, you have like a gusset, or you have like or like a blended radius or something like that, and you wanted the grain orientation to be normal to that gusset or that blended radius, you could potentially be able to manipulate the microstructure so that it orients to that, to be normal to that radius or that gusset, to be able to maximize the amount of mechanical performance of that feature. So this is an area of research that's going on that's really cool. It's happening at the fundamental science level, but this was achieved using additive manufacturing, and you really can't do this with any of the other manufacturing ways or easily. So this is a new area of application for AM. Also, tailored alloys for additive manufacturing. So traditionally, all of the materials and metals that have been used for additive processes have typically just been materials that have been used for castings, or they've been used for machinings. And those materials were developed many, many years ago for those applications. So people are now starting to take a step back and take a look at it and say, okay, what if those materials were optimized for those manufacturing methods? Surely additive, it cools at a different rate. It behaves differently from a metallic standpoint. Why can't materials also be designed and tailored for additive to take advantage of those quick cooling rates, for example, to sort of optimize the material itself or the technology? So that's also research that's happening at many of the universities and national labs around the world. So being able to take sort of those three ideas and then apply that to kind of an optimized sort of topology optimized structure that we talked about before really will take you to kind of the ultimate level of full advantage of AEM one day. And I think many of these already exist. So it's not unheard of to see some of these in practice that are kind of really taking advantage of AM. I know on the Curiosity rover, for example, they use functional gradient to be able to develop a column. So when the Curiosity rover will drop, take soil samples and drop it into it's a cylinder. They wanted to make that cylinder partially magnetic and not magnetic, and they didn't want to have like a whole extra magnet in an assembly that would traditionally perform that function attached to a tube. They wanted to make a single tube, and then they made it selectively magnetized so that inside of in the middle of the tube it was magnetic, and the other portions of the tube it was not. So it's a great example of by doing that, they were able to take weight out of that subassembly, which is obviously super important for the Curiosity rover. So that's a great example of using functioning gradient materials and really trying to optimize to reduce weight in an application. So some of these areas, even though it's kind of new researchy sort of happening, they're actually happening in some cases, and they will continue. This will continue to evolve, and CAD packages will be able to, one day select certain features to have specific type of materials and certain orientations and all of that stuff. That will all happen one day, and then again, I think we'll reach sort of this AM nirvana level where you can really truly optimize. Okay. So that's my pitch. I wanted to leave some time for questions, and because I'm sure you may have quite a few, but let's open it up for Q&A.
So before I pause the recording here, Dave, just two quick questions from me. So I feel like maybe this is just my view of manufacturing, but I feel like people get their ostrich heads in the dirt, and they
Mm-hmm.
either think traditional manufacturing or they think additive.
Yeah.
What do you think can drive people to blend those two together instead of just thinking one way or the other?
Yeah, I think it
Back to
could.
that white paper approach. How can they utilize
Yeah,
both the right way?
exactly. And I think it's not about. I think if you drive it back to this approach where you're breaking it down to the functional requirements, maybe here. You're if you're breaking it down to the functional requirements, then you can map those with what AM can do, and then you'll clearly start to realize what AM can't do, and then so that will then push you towards towards a more manufacturing traditional manufacturing approach to then fill in some of those gaps. But the main point is to be thinking about sort of AM up front so that you try to drive as much value out of it as you can. And then obviously there's areas where it can't achieve what you're looking for. Say, for example, like you need like a forged structure or something like that. And the mechanical properties of additive isn't going to quite get you there. You need a forging for that, for example. So, that would be an example of where traditional manufacturing you would need to use it, or maybe it's a glass structure or something like that where you need to have really nice transparency, but it needs to have sort of that the brittleness characteristics of sort of glass, for example, as a ceramic, and ceramic it's really tough to do additively, for example. So there's some areas obviously where you need to use that manufacturing, but I think starting from the beginning and functionally decomposing what you need to design will help you kind of sort that out.
Perfect.
Good question.
I'm going to go ahead and turn off the recording, and we'll let Alex ask his questions.